The other side of the story is equally weird. It's Gila monsters. These toxic lizards? NIDGK researchers went and started studying what Gila monsters, which can go for a really long time without eating, how do they regulate their sugar? And so they found a bunch of substances that really allow the Gila monsters to extend their metabolism for a long time.
Since you mentioned Ozempic, and I think many people would like to know more about it because it's all over the news right now. We all know its ability to help people lose weight, but you mentioned it in the context of diabetes. Does it really help to treat diabetes, or how Ozempic works in reality?
Ozempic is definitely better for diabetes than for weight loss. It was developed for diabetes, and then during the process of its testing, it was a beneficial side effect, that weight loss. Since then, a lot more has been done in other medicines that do actually more for weight loss than Ozempic does. So very, very quickly, going back to 1845, our friend Claude Bernard discovered this whole deal with glucose where you eat it and you can tolerate a lot, you inject it and you cannot tolerate a lot. So right around that time, people started speculating that there are hormones, additional hormones beyond insulin and glucagon, that are responsible for this effect. And Jean dubbed it incretin. And it basically was assumed to exist before it was actually found. And incretin is one or more hormones that are secreted by the intestine to aid in insulin secretion. And also, as it turns out, incretins are responsible for slowing down digestion. So your stomach contains your digestive juices and food, and so it parcels about 7 to 15 milliliters at a time into the intestine. There is a sphincter that opens and closes, and incretin controls the rate of opening and closing of that sphincter. And by the way, the reason why such small portions are released is because stomach is extremely acidic, and your intestine is actually fairly basic. But that balance is easy to shift. So if you release all at once, it basically will burn the intestine with acid. Intestine is alkalinized using bicarbonate, which incidentally also is secreted from the pancreas, because the pancreas is a dual-purpose gland. It secretes hormones into your blood, and it secretes gastric juice into your intestine. It contains digestive enzymes and bicarbonate. Anyway, somewhere between 1932 and 1960, people have started pointing out that there are all kinds of hormones, but still it was difficult to isolate them pure, that definitely stimulate insulin production when you eat. Right around 1980 is where things get really interesting. And things get really interesting from two alternative directions, and they both involve weird animals. One weird animal is the deep-sea anglerfish. So in 1982, a group of people, including people like Joel Haberner, Shields, and Lund, were collecting deep-sea anglerfish from fishermen. So they would go on boats, and during the normal fishing process, you sometimes pick up these anglerfish. They're hideously ugly, like weird little creatures. And in them, the cells that produce glucagon are easily identifiable. So they're easy to harvest. They would freeze them on dry ice and then dissect them later. Anyway, the point being is that the deep-sea anglerfish glucagon opened the door to studies of incretin, because incretin peptides are encoded essentially downstream in that organism. So you can find them real easily. And the studies...
Sorry, what do you mean they're encoded downstream? You have to unpack that.
If you consider DNA to be like the most basic analogy is your ticker tape that encodes instructions for things. So there are codes for glucagon and codes for incretin peptides. They're in close proximity to one another. They're basically right next to each other, which in general in organisms, that type of organization suggests functional involvement. It's not always the case, but often is. So if your instruction for making glucagon and some other peptide are close together, physically close on DNA, it's not a difficult assumption that other peptide is involved. And so they found glucagon and these GIP and GLP peptides in anglerfish in close proximity, encoded in tandem. So anyway, the one side, this opens the door for glucagon to be a therapeutic, because glucagon is actually a therapeutic. It's prescribed for critical hypoglycemia. When you run out of sugar, and even if you take glucose, you still low in sugar, you can inject glucagon and your body will release its own sugar from its stores, right? So it'll hydrolyze sugar polymers in your liver. One side of the story is deep-sea anglerfish, 1982. The other side of the story is equally weird. It's Gila monsters. These toxic lizards? NIDGK researchers went and started studying what Gila monsters, which can go for a really long time without eating, how do they regulate their sugar? And so they found a bunch of substances that really allow the Gila monsters to extend their metabolism for a long time. So they digest very slowly, they release sugar very slowly, but very steadily. And so they found these hormones that they called, among other things, extendin-4. They shopped them around, and the folks involved were John Pisano and John Eng. So they shopped them around, and interestingly, many pharma companies refused to pursue this direction. And the reason they refused is because they didn't want substances from toxic lizards to be in human pharmacopoeia. They were like not responsible. They were not going to be responsible for that, even though it's just silly. What does a substance from toxic lizard have to do with toxic lizard, really? Anyway, eventually a company named Amylin took this on and produced a drug in 2005 that they called Byetta.
And so the theory for why this was an interesting drug is that these lizards have I guess the idea is it's appetite suppressant because these lizards eat very rarely.
Among other things, yes, but it's more than appetite suppressant. Again, this
It's
is
about
diabetes.
sugar control.
This
It's
is
about
diabetes
glucose
drug.
control.
So what it did is it allowed people to regulate their insulin production. Rather than just injecting insulin, you could inject this stuff, and it would in turn regulate your insulin production and your glucose metabolism. So and still there are things that we don't understand, but at the time they certainly were interested in seeing how it goes. But Byetta was approved in 2005, and what people noticed is that it caused about 6% weight loss in people, 5-6%. And so they started realizing that this was interesting. In parallel, Novo Nordisk produced this medicine called Victoza, which was a daily injectable, also based on these peptides, on GAP peptides. Daily injectable was not so good, because it's annoying to inject yourself every day. But then up to 2017, they worked on making it progressively more stable and easier to preserve in the human body, so to speak. And so in 2010, Victoza, which is liraglutide, transformed into Ozempic, which is semaglutide, which is a modified peptide. And again, during the...
So they took the original hormone and modified it to make it hard to break down.
Hard to break down, more prolonged mode of action. Because among other things, injection of these hormones in the early days, they would cause like uncontrolled vomiting, for example, horrible nausea. It wasn't so great. So over the process of development, this transformed into what we now know.
Let's say you're injecting people with this, they're having uncontrolled vomiting. What do you do? What's next? Like, what's your next guess? What's your next move? How do you connect this vomiting to the structure of or you know what I'm saying? Like,
among other things, I wasn't there doing it, but I would not be surprised if they did dose dependency studies. And they found out that, for example, for different people, the doses are slightly variable. So in this case, what you want to do is you want to slow the uptake. So you want to make sure that even if you inadvertently give a slightly higher dose than what you wanted, because you can't really dial it in for every individual person. We can't all be Jeff Bezos who can afford to do that, right? So a physician of a very wealthy person can spend 6 months dialing to the T the exact regimen of something. So you, being the wealthy patron, are going to pay me to study you for a year and tell you that you don't need 0.25 milligrams of Ozempic. You need 0.17 milligrams unless you ran that day, and then you need 0.36. So you work out this precise, very, very detailed regimen, but it's certainly not for everyone, right? You can't sell it to millions of people. It's not going to work that way because you can't afford to spend the time.